Hello, everyone. Thanks for joining us. We really appreciate you joining us for our August webinar. Today we are going to discuss the CPC blues, several modifications of the CPC blues in a variety of application areas. We will be recording this session, so all of those in attendance today will get a link to the recording as well as the PDF of the presentation. And as always, if you have any questions along the way, feel free to use the chat box. But if that's not your thing, go ahead and shoot me an email, and I'd be happy to help at the end. All right, with that, I'll go ahead and get started. I will go off screen a little bit here for the talk. So we will talk about the CPC blues, and as we have done in the past, the CPC blues, of course, are metal complexes as part of the organic pigment categorization in the overall world of colorants. Screen's not working here. Okay. In terms of color space, we typically use the words green shade and red shade when talking about the color space of blue pigments. And for the CPC blues, typically the alphas are the more red shade, and the betas are the more green shade in color space. The epsilon, the pigment blue 15-6, is always going to be the reddest version of the CPC blues. So you can kind of get a feel for where they fit in overall color space. And again, this is more of a generality. The color will develop differently in each of your application areas and formulations and dispersion techniques. But in general, these are where they fall in terms of color space. So crystal modifications, or polymorphism to be a little bit more technically correct, happens a lot in a lot of different pigment chemistries. And it really is a term that describes that a chemistry can exhibit more than one modification or crystal structure. The CPC blues are an example of this, where there are many different forms, as you can see here, with the pretty much a very long list of Greek alphabet letters. However, there's only 3 that are particularly commercially available, but the alpha and the beta have the most commercial importance overall. The epsilon is available, but it is losing favor in the pigment world in favor of the alphas and the betas. So for the CPC blues, the crystal modification shows itself in terms of the how much overlap the copper ion in the middle of the structure are to each other. So when there is a lot of overlap or more overlap, thus a smaller distance between the two copper atoms in there, these are going to be the alphas, which is the 15 zeros, or sometimes you just see it as pigment blue 15, the 15 ones and twos. When that spacing or overlap is when there is less overlap or more spacing, these are going to be the betas, the 15 3s and 4s. All of these blues will start out with the same crude copper phthalocyanine as a starting ingredient. All of the polymorphisms that we are talking about today will always start with the same material. However, it is the quality and the quality and the nature of the crude that helps define which crystal structure you'll receive in the end. So just a little bit more of a clarification with respect to the crystal structures. As I mentioned, the alphas are the 15 zeros, ones, and twos. Betas are the 15 threes and fours. They're the greener ones. And the epsilon blue, which is the most red, is the pigment blue 15-6. So these crystal structures, were the overlapping of the copper atoms in the structure, are all defined on how the crude is handled in the beginning stages of the pigmentation process. For the alpha blues, the first step for that crude is to fully dissolve that into sulfuric acid. And this is a terminology that is used, and it's called acid pasting. And once that crude is completely dissolved, it's then precipitated out to be able to create the alpha blue particles. So it's this precipitation process that aligns the copper atoms as they need to be for those alpha pigments. Once the particles are precipitated out, they are filtered and re-slurried to provide a good uniform slurry. And at this point, those crystals then begin to grow in the pigmentation steps. And in some cases, surface treatments are used, or chemical surface treatments are used, all depending on the end application area. And then the mechanical finishing steps of drying and pulverization are then applied to create the final product for the targeted end application area. For those of you who are a little bit more visual, like myself, a little visual on how the crude becomes a final pigment. The crude itself is very large in size. In the alpha process, once that crude has been dissolved and precipitated out, you see very, very fine particles that are achieved and ready to be to go through the pigmentation step. And then in the end, the final particles sizes, as well as the surface treatments and other mechanical finishing steps are applied. The opposite is the beta blues. So in this case, the same crude, is not dissolved like the alpha process, but it is milled down to a smaller size, and typically that's done in a ball mill or in a tritter, so that particle size is reduced. Once that's completed, then the pigmentation process starts there, where the crystal is grown to the appropriate size. Sometimes that's done with surfactant to be able to get to that end size for the desired end application. Once the pigmentation is completed, the slurry is then purified to get the solvent out, and any additional chemical surface treatments are used for that particular product. And then, of course, the mechanical filtration, drying, and pulverization finishing is also applied for that end product requirements. Same pictures to start with, the same copper, the crude. However, once the milling is complete, you see a little different shape as far as the beginnings of the process for betas. The particle size and shape are smaller, but they are also a little bit more ragged. This is the material that goes through that pigmentation step to create the final product. And we've always talked about this, and it's always good to continue to remind us that the bulk of the performance of the pigment is always going to be determined by the chemistry. And it is then the finishing, whether it be a chemical finishing like a surface treatment or an additive, or whether it is a mechanical finishing by drying and pulverization, that just shifts the performance in one direction of or another. But it does enough in that shift to be able to see differences in each of the application areas. So I mentioned about the finishing part of it. So there are several places where finishing can be applied to a pigment. On the chemical side, it can be done right after the crystallization occurs in the reactors. Or it also can be done at the very end in the blending stage, where various additives may be added for that particular product. Mechanical finishing is really dictated by the choice of the type of dryer that is used. That also helps with determining how hard the particles are going to be, as well as what some of that bulk density might be. And then from a particle size and size distribution perspective, the choice of which type of pulverization is done is also another option in terms of mechanical finishing. So we've always talked about finishing and how they impact the application areas. And you've heard me say this more than once, that all of these pigments, although they were designed for a specific end application, they can be used in cross applications as well, depending on what you're looking for. In a lot of cases where you might want to optimize a particular property, you may want to look at a different product that was not necessarily designed or developed for the application that you're working in, but maybe something else. So they will all work. They will just provide you with different properties that may or may not be what you're looking for in there. However, some generalities with respect to application areas in pigments, in plastics applications, because the residence time of the dispersion process is very short. We need to make sure that the pigment particle itself is, I call it clean as possible in terms of additives and things like that. It needs to be as soft as it can be and as small as it can be, so that polymer dispersion process is optimized as best as we can make it. Coatings and inks, they're very similar in nature because there's a wide variety of types of formulations that are used, all the way from powder coatings to liquid coatings, water, solvent, and also in each sub-application, there's a variety of formulation types. So when you look at a general brochure for pigments, you'll notice a lot of options with respect to pigments that were developed for coatings and inks. Because of this reason, there's so many formulations that we try to make sure that we have pigments that are optimized for some of these areas. So if we take a look at the subject matter that we're talking about, the modifications in the copper phthalocyanine chemistries, and in each area we're going to see some differences, and that's what we would like to discuss with you today. So if we start out with plastics areas, and we first take a look at the color development. So what we did is we took a look at these 6 different product types the alphas, the betas, and the epsilon in mass tone. And these, the data that I have here in this particular chart are an average of a number of products in each of these modification areas, so we can get a better feel for where they fit in terms of color space. So I showed you the initial chart earlier about color space and where they fit in, and that was definitely a big generality. Here we have the opportunity to take a look at a more application specific averages for these particular areas. So in terms of plastics with respect to mass tone, we do see that the pigment blues 15.6, the epsilon, does show to be the most red of all of the six categories here. The alphas are sort of in between. We do see the pigment blue 15.0 as being still very red, almost as red as the epsilon. On the beta side, it's no surprise that the pigment blue 15.4 is the most green, because that is in general what we see with respect to that particular type of modification. Interestingly enough, the 15.3, which is a beta and should be a little bit more to the green side, but on average, this does show to be more on the red side, which may be an indication that, again, there's multiple products within this category, so that there might be some that are less than optimal in terms of dispersion, that's pushing that more to the red side versus to the desired green side. On the tint tone, a little bit more about what we would expect with respect to color positioning. The epsilon 15.6 is very red. The alphas are next in red, and the betas are on the green side. The number in the bubble itself is the L value, so a measure of the strength of these types of chemistries within this plastic formulation. And one of the things to note directly is the alphas are provide with the most strength in this particular formulation, along with the actual 15.3 beta. They will be the most dispersible, if you will, in this formulation, so they'll develop the most strength. On the flip side is the 15.2, 15.4. They are going to be your weaker ones, which is not surprising, as these two chemistries tend to be more directed at coatings formulations and not plastic formulations. If we take a bigger look at in terms of the finishing with the pigment blue 15.3s in plastics, we have 9 products in different categories. Like I said, there's plastics coatings, regular ink, and inkjet products in this category. So we can see how the various finishing techniques, whether they be chemical or mechanical, impact that color development in a plastic formulation. So the first thing to notice here is that there is a wide variety of color and development in here in terms of the amount of redness or greenness in here. And so if you remember back to the original average of the plastics area, we saw that the redness of the pigment blue 15.3 was uncharacteristically to the redder side. And basically what we see here is we can see where the other products in the other application areas drive that closer to the red side versus the green side with these areas. But they all work. They just offer something a little bit differently. And similarly, in terms of the tint tone for these Pigment Blue 15-3s in the plastic formulation, they do also span a little bit more of the space. However, if you notice the scale of the chart is a little bit more narrow with respect to the redness and the greenness. We do have one product that is, very is much more green, and one product that is much more red with respect to tint tone. And in terms of the strength or tint tone L values, when I look at all of these, they're pretty close in number value, suggesting that they do disperse fairly well and similarly to each other. Performance, so technical performance in terms of dispersibility. Filter pressure value is a very good measure to help us determine how well the particular product and chemistry disperses within the polymer matrix. So here are all of the products that went into the study that we've done. One thing I did not do, like I did with a color, is I did not do an average across the modifications, primarily because they all perform very differently in here. So it's probably not a fair thing to compare modifications, especially when the finishing techniques impacts the dispersibility in a large amount in here. So you can see how the differences in terms of chemistry are all over the board with respect to filter pressure values. Some are very good, some are a little less in terms of dispersibility in there. So depending on where you're looking in there. But if we focus again at the Pigment Blue 15-3 products, we see a wide variety of performance areas. I placed a line at 2 bars per gram of pigment in terms of filter pressure value, primarily because we use that as a criteria for products that might be suitable for more stringent fiber and film application areas, as well as just general plastic application areas. So the interesting thing to note is that, yes, the products that were developed for plastics certainly have that good filter pressure value, but also there are 2 coatings, 2 products that were developed for coatings, and 1 inkjet product that was developed that also have very good filter pressure value. So options exist, but in the same vein, the other Blue 15-3 that was developed for inkjet has a very poor filter pressure value in here. So matching up the performance is key in what you're looking for. So moving on to coatings, I put together 2 types of both solvent-based industrial types of coatings, as well as a water-based decorative type of coatings, and doing the same type of investigation for these CPC blues. So like we've done before, here is the average of the 6 modifications with respect to, in this case, it's a deep tint tone color positioning, which is a 50-50 mix with TiO2. To be able to better see the color differences of these developments. So overall, when we look at this, so this is sort of a kind of a dark tint tone in terms of a color space. Again, the Epsilon, the Pigment Blue 15-6, is still going to be your most red, followed by some alphas and the betas. The interesting thing to note here that in this solvent-based polyurethane formulation type, the pigment blue 15 0 alpha does not disperse as well because it shows itself to be very to the green side, as well as a higher L value in terms of its development. So in this formulation type, this modification and product does not disperse as well as the others. In the standard tint tone formulation, same idea here. The materials or the modifications fall into color space as we would expect, with the epsilon being the most red, the alphas in the next most red, and the betas being to the green side. Again, the 15-0 demonstrates that it does not disperse as well with that higher tint tone L value. In a metallic formulation, I have data for the alphas and the betas in this particular case, so that you can get a feel for how much color travel you'll see overall in terms of these modifications. The alphas, the 15-1 and 15-2, will have more overall color travel, both in the green to red transition as well as the blue to yellow transition, and the betas will provide more green to red transition and less of the blue to yellow transition. If we focus again on those same 9 Pigment Blue 15-3 products in this 2K solvent-based polyurethane formulation, to get a feel for how the overall impact of the finishing techniques occur. So these are the same 9 that we saw in the plastics, which were a little bit more spaced out in terms of their positioning. But here again, we see a variety of redness and greenness. Here we have a scale of about 2 units across all of these products, as well as a number of the blue to yellow. So again, another 2 units between the most blue versus the most yellow in this particular case. We do have one product that was originally developed for an ink application area that shows to be very green, almost as green as we would expect a Pigment Blue 15-4 to be. The remaining products kind of fall into a close category to the redder side. And on the tint tone L, or the tint tone formulation with the TiO2 at a 1090 formulation area, we see a similar pattern here. Again, that one ink developed product being still to the very green side. The remaining ones kind of fall into a close pattern, but a variety of responses depending on what you're looking for. Color travel, like we saw with all the indexes here. Here we get to see where how the finishing impacts that color travel of the Pigment Blue 15-3. If you recall, we mentioned that the betas have the most red to green travel and the least blue to yellow travel. So when we take a look at just the products in that 15-3 category, we see a variety of differences here as well. The bulk of them all look about the same. However, we do have one ink product that does travel more than the others. The plastic, one of the plastics created materials does have less travel in there. So again, some options to consider when developing a formulation. If we look at water-based in the decorative area, we see some interesting trends as well. Again, the same type of thing that we saw before with all of the product averages in a mass tone type formulation. Similar to what we saw in the plastics area, where, of course, the epsilon 15.6 is still going to provide the most redness. The alphas are in the middle. The blue 15.4 is the most green, and that the average of the 15.3s is more toward the red side. Kind of looks like the alphas in this particular space and formulation. On the tint tone area, again, just like we would expect, they fall into line in terms of color space. The 15.6 epsilon is still very, very red. All of the alphas are similar in terms of their redness, and then the betas are to the green side. And when we look at the L value, which is, as I mentioned, another measure of strength, we see that the alphas tend to provide the most strength in this formulation. The epsilon also being very red, but also provides a very good strength in here. And then the betas are less in terms of their strength value. And then focusing on the 15.3s in this water-based decorative formulation, similar to what we've seen before. We have this one product that still is also very green in this formulation as well. So overall, in all formulations, it does show up to be very green. The other products have a variety of color positionings depending on what might be appropriate for your formulation. And then in the tint tone, again, we see something very similar for what we've seen in the other application areas, with the one product being that was developed for the ink applications, still to the green side, but a little less on the L value in terms of the strength. Powder coatings is one area that is always kind of a crossover. Sometimes it resembles more plastics application because of the dispersion, residence time, but it also has a lot of connections to liquid color development as well. Primarily because there's a lot of need to be able to color match from one to the other. So in this case, we take a look at, I have data on the alphas and the betas in terms of average and color positioning. So something similar that we've seen in other application areas. The alphas tend to be still on the red side, and then a little bit more difference between the beta products in terms of how much redness is available, or greenness in terms of in this particular case. In the tint tone, as expected, the alphas are to the red side, with the Pigment Blue 15.1 providing the most strength, and as well as on the beta side, they're both still to the green side and very similar in terms of their strength development. The Pigment Blue 15.2 is not typically a powder coating designed product. This is more developed for liquid coatings. However, it does work. If we take a look at finishing in terms of the 15.3 areas, here, in this particular case, we have data on a plastic one, a couple of coatings ones, and an ink one in here. So we can see that there is definitely some color development differences between these product types in this chemistry space. and in the tint tone area as well, all except for that one ink grade. They are pretty much the same in terms of its color space. We have options with a very green Pigment Blue 15-3 as well. From a performance perspective, I included a couple of performance aspects of it. The first being pellet flow. So on average, when I look at these three different types of letdowns, the 1090 tint, the deep tint tone of 50/50 TiO2, and the a carbon black letdown, so a 98 to carbon black. There's not a lot of difference between the pellet flow of these chemistries. A little bit more shows up with respect to high TiO2 loadings in there. The error bars that I have on here are really just a guide for a plus or minus 10% value, so you can kind of get a feel for how much crossover and what variability there are between these chemistries. So all in all, I would say in all but the 1090, there might be some difference between the chemistries in here. And overbake stability, here we do see some differences between the four different chemistries in this formulation. Overall, the Pigment Blue 15-1 is a very rugged modification for powder coatings. So this overbase stability is 220 degrees C for 60 minutes in here. So it's quite a harsh test method. So when TiO2 is available, present in the formulation for the 15, 2, 3, and 4, it does show some influence to the color shift during an overbake scenario. Not so much with respect to a more of a mass tone or with carbon black as well. So at this point, I'd just like to say thank you. If you have any questions along the way, you can feel free to reach out to any one of our team. We'd be happy to help. As far as next month, we're not going to be doing a webinar, but we hope to see you at two technical conferences, the Coatings Trends and Technology Summit in the beginning of September, and then the CAD Retech near the end of September. Sudarshan will be at both, and we will be doing some technical presentations at each one of them. So we hope to see you there. At this point, I'd like to say thank you again for sharing your time with us. We really appreciate it and your input. At this point, I'd like to open it up to any questions that you might have. So if you do have any questions, feel free to use the chat box.